So this is an introduction to Riemann sums. Now we've done 2 lessons on antiderivatives. So we're going to take a break on antiderivatives for a few lessons just to learn a little bit about why we're going to do some antiderivatives. So there's some backstory here, and so this might be a little bit longer of a video, and then the homework assignment will be a little bit less, which I'm sure you're going to be okay with. So what we're going to try to do is take a look at this particular curve, which is 16 minus x squared. And what we're going to try to do is find the area underneath that curve. Okay? So what we can do is we can try approximating it using rectangles. We could use one rectangle, and you can see that this rectangle has a width of 4 and a height of 16. So therefore, that rectangle has an area of 64. You can see it right here in this I equals 64. Okay? All right, so how many people feel like that's a good estimation? Well, I can't count your hands because I can't see you. But what we're going to do here is we're going to probably say no. No, that's definitely not. We've got all that green area above the curve that's not really a good approximation. So I'm going to go and change the number of rectangles. And all of a sudden, if I used 2 rectangles, I've got a rectangle that is 2 wide, that's 16 tall, that's 32. And I've got another rectangle that's 2 wide, that is, looks like it's about 12 tall. So that's 24. So that's 8 less. That's going to be 56. So that's, I mean, it's still not good. We've got a lot of green space there. And really what's happening is we're not actually going to use 2 rectangles either. And we're not going to use 3 or 4 or 5 or 6. But as we increase the number of rectangles, you can see that the extra area, those little green steps, if you will, it's almost like a staircase, a curved staircase. As I increase the number of rectangles, the area of all of those rectangles combined is getting closer and closer to the actual area under the curve. So what we're going to do with that is I'm going to show you how it works for a small number of rectangles before we get into how it works for a large number of rectangles. And I'm going to change the function. So I'm going to say, let's use f of x is equal to 4 minus x squared. All right. And we're going to go from 0 to 2. So that function looks like this. Actually, I'm going to use my scale on the x-axis to be a half. 1, 2, 3, 4. So we're here, we plug in 1, we get out 3. We plug in 2, we get out 0. So that's the curve, sort of. And we're trying to find the area. Okay? Now I'm going to copy that because I'm going to use it a couple times. Now if I wanted to, I want length times width for n rectangles. So if we were going to use 1 rectangle, here's what it would look like. We could put the height of the rectangle on the left, or in the center, or on the right. So I'm going to do this down here. Let's just do it on the left. I missed the T here. If I made the height of this rectangle on the left of this interval from 0 to 2, here's my rectangle. The height would be on the left here, and the rectangle would look like this. Okay? And we would get height equals, well, that would be the left-hand point is 0, right? That's the x value. And we're going to plug it into my function, which is 4 minus x squared. So 4 minus 0 squared. The height is 4. Now, how wide is that? The width is how wide is my interval. So that's the end point minus the starting point divided by the number of rectangles. Gives me the width of my rectangle. So 2 minus 0 is 2 divided by 1. The width is 2. So I'm going to multiply, obviously, the area of a rectangle is 4 width times height, and we get 8. So an estimate of the area of that curve would be 8 if I used one rectangle and I used a left-hand endpoint. It would change significantly if I used a right-hand endpoint. Let's check that out real quick. So same drawing. I need to draw a rectangle here on with the height, a width of 2, and the height at the very far right. Okay, so I'm going to do the height again is f of where my endpoint is. 4 minus 2 squared is 0. That's interesting. And the width is 2 minus 0. So the endpoint minus the starting point divided by how many rectangles. And that would be 2. Now it's not going to matter because 0 times 2 is 0. So the area of that rectangle is 0. Let's try one in the middle. So the value halfway between my starting point and my ending point would be 1. We can go to the middle of this and say, here's my rectangle. So again, the height is f of 1. Function is 4 minus x squared, 4 minus 1 squared. I get a height of 3. And the width, again, the width, I'm going to help you out a little bit here. The interval is always a to b, and the width is always going to be b minus a over n. Okay, the ending value in my interval, the starting value, and the number of rectangles. So in this case, 2 minus 0 over 1 gives me a width of 2. Multiply those to get my area of that one rectangle to be 6. So out of those three, obviously 0 is way off. 8 is clearly too much. This one, you can kind of see that whatever we miss over here, we add over here. So it's probably the closest estimate. So this 6 is probably the closest estimate. However, we don't want to use 1. So let's use the same function, same interval, 4 minus x squared from 0 to 2, and let's take a look at what it looks like with 4 rectangles. Okay, so first of all, let's find the width, because the width is going to be consistent all the way through for this type of problem, right? So again, b minus a over n, 2 minus 0 over n, 2 minus 0 over 4, 2 over 4. The width of each of those rectangles is going to be not 1 over 5, 1 over 2. Okay, so what I'm looking to have here, I'm going to color code each rectangle. First one I'm going to do purple. So there's the width of the first rectangle. Then I'll do green. The width of the second. I'll do orange, just so that they can all stand out visually. Okay, so I need a rectangle at each of those things. Honestly, I prefer to do right-hand endpoints. So when I draw my right-hand endpoints, I'm going to go all the way up to the curve there and draw my rectangle. So my first rectangle looks like that. My second rectangle, height is on the right. Oof. I'm going to zoom in a little bit, make it a little bit better for you. Okay. And then orange, height here. And then red, height there. Okay, so actually that red line is actually the rectangle for the last one. So let's take a look. Let's see what we're going to get. So rectangle 1, which is the purple, we need the height of that rectangle. So we need to look and see what the x coordinate is. Well, the width is 1/2. From here to here is 1/2. We start at 0, we end at 1/2. So we need to find f of 1/2. The width of every single one of these is 1/2. Okay, so I'm going to actually make a little chart for all of these. So rectangle number, height, width, area, and hopefully we're going to use this and get a more accurate answer. So rectangle 1, the height is f of 1/2, so it's 4 minus 1/2 squared. Okay, moving things over because I'm not going to have enough room to do that. 4 minus 1/4 is 15/4. And the width is 1/2. So the area, multiplying those together, would give me 15/8. So this rectangle right here is 15/8. Rectangle 2, green. Four minus the x value of the height is at 1. So I'm going to plug in 1. This one's a little bit better. I get 3 times the 1/2 gives me 3/2, which is the same as 12/8. I'm going to keep them all as a common denominator. I think we have orange next. So the orange height happens at 1.5. Okay, this is just the number of the rectangles here, not anything other than that. So 4 minus 3/2 squared, that's 4 minus 9/4, 16/4 minus 9/4 is 7/4 times 1/2 is 7/8. Okay, that is 7/8. I didn't color in the green one. This one was 12/8. And clearly, you can see the area of the red to be 0, but here's why. 4 minus the x value of that height is at 2. 2 squared is 4. So we get a height of 0 times 1/2 is 0. Now to get the actual area, we're going to add, and this is the Greek letter sigma, the sum of all of those rectangles is our approximate area. Now clearly it's not great, but hopefully it's better than what we had before. Oh yeah, I want to use that same color. 15, 27, 34 over 8, or 17/4 is our approximate area. Okay, now hopefully we have some error in here, right? There's a missing chunk here, a missing chunk there, a missing chunk there, and a huge missing chunk there. I'm not sure if this answer, 17/4, is closer than 6. But that's not the point. We're really going to be just using this as an example, and then later on using a theoretical approach to use an infinite number of rectangles. So this is just the basis.